All right, everyone. Sorry about that. Okay, sorry about that. Second I hit record, I have to clear my throat. Try not to do that on the microphone. Goodness, I'm uh, I'm over this weather change. I, for whatever reason, can't seem to kick this little tiny bit of congestion that isn't troublesome, except for when I go to talk for a while. Anyway, there was a question here asking what is going on with this second folder here. Called quaternion test. Okay, the that folder there is for something that we haven't talked about yet, and we're short on class periods, so I don't know if we'll be able to go into the full detail of how those things work, but we can discuss what's going on with them. But the idea behind them is these are what are referred to as unit tests. Okay. Once we have gone through and understand classes, one of the things that we can do with classes is, and this is integrated into MATLAB, is to write unit tests. The purpose of unit tests are to evaluate a set of functions, or in this case, a class, under a bunch of different conditions. Okay. The purpose of the test is that you perform a computation or a function call or something like that, and then you have a condition that is either true or false based on the results of the function calls that you have made. The idea behind this is that you write the tests with the intention of knowing what the behavior of the program should be, and then you modify the program until it is able to pass the tests. So we have not this semester programmed this way, but one of the ideas that you can use as you're going through and doing computer software development is called test-driven development. The idea is that you start off with a set of goals for the program, a set of behaviors that it's supposed to have, features that it is supposed to contain. You write tests that test whether or not these features have been implemented correctly and produce the correct results. And then you work backwards from that point to actually develop the code to pass the tests. So you don't write the code first, you write the tests first, and the code isn't done until it can pass all the tests. Yeah. It's not something that we've done because you have to have the ability and the programming knowledge to write the tests before you go backwards and write all the code. So it's like a second semester at minimum sort of thing, at least in my opinion. Because from here, we're starting from a baseline of you may have not written a computer program before. But the other thing is that for the MATLAB version of this in particular, you have to know how classes work because it's implemented in MATLAB as a class. And of course, we didn't get to that until the very end of our semester here. Okay, so what you're looking at on screen are various tests that are written for the quaternion class. Several of these tests are designed to check the inputs to the functions and methods that you're supposed to write for the assignment, and I'll talk a little bit more about that here in a second. And these other tests down here are designed to do the computations in using the matrix rotation idea that we talked about beforehand, and then compare the results. So if you do the rotation with respect to the quaternions correctly, then what will happen is it should be within some small amount of error, the same as doing the rotation with matrices, 3x3 matrices, the rotation matrices that we talked about last class. And so these results are compared numerically. That's what the whole point of this is. We, in this instance, use verify statements, which are special methods for this unit testing class. This verify checks to see if this statement here is less than this value. So what I do is I do the computation using the quaternion class. What I should get back is a vector that's in 3D. Okay. I compute an expected solution, which is me knowing the answer to the question by doing the rotation using 3D rotations and then creating a quaternion out of that rotated vector. And then I take the norm of the difference between those two vectors and check to see that that length is a small number. If the vectors are about the same, the length of the difference of those vectors should be almost zero. Okay. And the way that the rotation method works for the class is that or for the function that I want you to write, it has different behaviors based on what inputs it's given. Okay, which is why there's so many different tests here. Okay, so the idea is that if we run the tests, some of the tests pass and some of the tests fail. Okay. Ideally, we want to pass all the tests, but in order for that to work, we need all of the methods in our class to be implemented, right? And so there's some issues with the code here that didn't quite work out. I'll double check this to make sure that everything's in order before I upload this, but that's the idea. Okay. Yeah. Um, okay, so the question for the video, if you couldn't hear, was more or less what's the goal and what is the overall idea behind how we're supposed to use these tests. Okay. The first thing that I want to say is that I'm mostly talking about this because it's in the folder, and someone else asked about it. Okay. I'm not sure we're going to have time to use this all this way and to worry about passing all these tests because of the way that our semester ended up working out a little bit differently than previous semesters where this project was originated. Generally, what you would do if you were talking about test-driven development is you would work on it in the way that you described, which would be to you would start off by getting the basic functionality of your program working, and after you get to a certain point, then you should be able to pass some of the basic tests. And what you would do is, of course, you would write this giant test battery, starting with having tests checking for simple things, and then building up and having more and more complicated tests. So some tests are supposed to check the inputs and outputs to make sure that the inputs and outputs are right. You would have other tests that check specific types of computations, things that were easy, things that were hard, and so on. And the point of the tests is that, pardon me, as you go through and are writing your program, you have the ability to check to make sure that you haven't made a change that makes one of the easy tests stop working. Okay, so if you get it to do something basic and you keep going and you realize later on that it's not working for whatever reason, for the harder stuff and you have to make changes, you don't want to give up the fact that the old tests don't work. You don't want to miss that something's wrong that should be simple or whatever. So it allows you to track your progress in every direction simultaneously, as opposed to having to go through and kind of hand check to see how this stuff works. Okay, so it gives you a very robust set of things, assuming that you go through the trouble of writing enough tests to check all of these things. And so you don't accidentally lose track of simple stuff. All right, I do apologize for those of you who are listening on the microphone. I a little bit more colicky today than I can seem to keep a handle on. All right. So for the purposes for now, we're going to set the test aside. Okay. If I want to talk about if we want to bring those back later, then that'll be something that we discuss maybe next week or what have you. But not a major concern. I just didn't want to not answer the question that was asked about them. Okay. Now, what I will do here later on, I know I said I was going to do this before the weekend, but didn't have time to check everything I needed to get checked to make sure that this all worked. But there is a notes page that's written up that will be linked in Blackboard along with this assignment here that summarizes a lot of our in-class discussion about quaternions and rotations and sets up the two functions that I'm going to, or the two methods that I want you to write that will be for our quaternion class. And I will make the modifications to the base quaternion file that I said I was going to make, so that all you'll need to do is write the separate M files that go along with this, okay, according to these specifications. And one of the things that I want to double check on is to make sure that the instructions here don't have any errors in them. Okay, but this is the gist of it. You're going to be writing two functions. Okay, one of the functions is going to be to generate a rotation quaternion. Okay, rotation quaternions have this form here, and this is it's a matter of taking the inputs for n and theta, making sure that n is a unit vector, and using the constructor here to generate, using the constructor for the quaternion class in order to generate a vector or a quaternion in this form. Is it's a plus bi plus cj plus dk, right? So you just need to make sure that nx, ny, and z are form a unit vector. So the sum of their squares has to be equal to 1. Okay, the easiest way to do that is to divide by their length. And then the sine of theta over 2 gets distributed to each of those factors when you construct your rotation quaternion. Okay. The second of these functions is going to be a little bit more involved. Okay. What I want you to do here is to write a function that has variegin, okay, as one of its inputs. This function is going to be working so that it has two modes. One of the modes is going to be if variegin is just equal to q, which means you have created your rotation quaternion before you make this function call. So it'll be rotate pq, and p is the vector quaternion and q is the rotation quaternion. Okay. The second mode is when variegin equals n theta, where n and theta have to follow the same rules as they do for the previous function. Make sense? Yeah. And so the idea for the second version of this is that if you don't have the rotation quaternion made beforehand, you call the other function that you have written in order to make the rotation quaternion, and then do the product to do the rotation, where this, of course, right here is the rotation product, and we demonstrated that that worked last class. Make sense? Okay. All right. All right. And then pay attention to this note here about how you have to invoke this function. We haven't talked about this yet. I'll talk about it briefly here in a second. But for classes, there are designations of types of methods for classes. The main designations are private, public, and static. Okay, and private and public obviously are kind of opposites of one another, and then static methods are their own thing. Okay. A static method is a method of a class that is just a regular function. Okay. You have to, because one of the inputs of the function is not itself a quaternion, MATLAB doesn't default to trying to imagine that that thing is a method of the quaternion class. So it has to be told that it's a method of the quaternion class because its inputs are do not involve a quaternion, and it's not the constructor, so it's not named the same thing as the class. Does that make sense? Okay. The main idea here is that when we use classes for computations and programming, a bunch of stuff is context dependent. So if I go into MATLAB and I type in like 2 plus 3, okay, MATLAB knows what to do because it knows what class 2 is and what class 3 is and what it means when I say add this double to this other double, right? Now, I could also have an integer 5 and an integer 2 and say add these two integers together, and MATLAB knows what to do because they're both integers and there's a method for adding integers together. But the thing that MATLAB technically does differs based on the classes that those data objects are elements of, right? And I've told you that in MATLAB, when we type this, what really happens is that MATLAB is calling this function, right? Now, there are many different plus functions that exist in MATLAB that all do different things based on what type of inputs they're given. Those functions have the same name. They do not do the same thing. Now, they look like they do the same thing because I added the same two numbers together as far as we're concerned, right? Okay. We'll do it this way. Okay. Double is a class in MATLAB, right? So is a 32-bit integer. Okay. Those two different classes have two different implementations of the plus method. Okay. MATLAB knows which one to use because when I typed this, the input was an element of the 32-bit integer class. Okay. When I typed the other version, it was an element or the double class. Here, for my rotation quaternion method, when I go to use that, if I just type rotation quaternion, MATLAB doesn't know to check the list of quaternion function things because neither n nor theta are going to be elements of the class. All right. So this bit here is to tell MATLAB, this is a method of this class, do this thing. All right. You don't have the context there because one of the inputs doesn't have the virtue of being the element of the class. For the other stuff that we've done where I just take two quaternions and add them together, it knows to use that plus because one of those things is a quaternion, and that's the only way this makes sense. All right. Okay. And then also on this notes page, just as a thing that you can use, and you should make up your own examples to go along with this, it shows you a plot of the rotation so that you can see the point in space, you can see the axis that you've chosen, and the arc that is made as that point is rotated on the sphere. Okay. And there's a partial version of this up here, and then the whole thing with the full arc. Okay. All right. So questions about this? I know it'll be easier to ask questions after you have an opportunity to take a look at this, but wanted to check before moving on here. Okay. All right. So what I'm going to want you to do is I'm going to make some changes to the code here to make sure that it is set up for what it needs to have. Okay. And the part that you're going to be responsible for is adding the two M files to this that go along that represent those methods. Okay. And then one of the things that I will do before I post this and send somebody off on a path of ruin is double check to make sure that the tests will work according to the conditions that are typed up in the notes page and everything, but didn't quite get all that all the way taken care of. Well, what do you mean? Okay. So these lines here are part of it, right? So what I want as an output is the rotation quaternion, which is this thing. Okay, but it'll be obviously a numerical quaternion element of the class. Okay, the inputs are described here with theta being given in radians and n being some 3 vector. Now the inputs for n are allowed to not be a unit vector when they're entered. Part of your job is to divide by the length and turn it into a unit vector if it's not. So if I give you the vector 1, 2, negative 3, then your program should still generate a proper rotation quaternion by turning that vector into a unit vector and using it here. Okay. For the second one, same or similar deal. The two different forms of var again are discussed down here, and I talked a little bit about what the differences between those two are, right? And the output that you're going to get is the quaternion from the rotation. It ought to have this form because it's supposed to represent a point in 3D space. All right. Does that help? Okay. Okay. having a bit of a hard time here. Okay. So the question is, what do you turn in? You're going to turn in two M files. You're going to turn in a rotate.m and a rotation quaternion.m. Those two M files are going to sit alongside quaternion.m here inside of this @quaternion folder. Okay. So you can give me the whole folder, or you can just give me the two M files. Either way, but the thing that you're making that's new are the two M files. You shouldn't have to touch quaternion.m other than to look inside of it and make sure that, you shouldn't have to modify the quaternion.m file. You can use its method. You're going to have to use its methods. Is that your question? Huh? The problem with cough drops is that I have a microphone right next to my face, so I can't have that in my mouth. It's a hassle trying to talk. Anyway, sorry, the interruptions are because I don't know, my face with the mask on is real humid and it's bothering me. Okay. All right. I'm sorry. I want to answer your question. Yeah. So just to be more careful about what I said about not needing to touch the quaternion.m file. Of course, you can take a peek and use it as a guide to help you figure out how to program things. And to make sure that the methods that you have written work the way that they're intended. But for your M files that you're writing to turn in, you should not modify anything in a quaternion.m file. Okay. If you make a modification and your M files don't work unless that modification is there, then it's outside of the parameters of the assignment. Okay. Alrighty. So that will be one of the assignments that we have to finish things off for the semester. And then the other one will be something that requires a little bit of setup. And so we need to talk through that. Okay. I've written up a notes page for this to describe what's going on here. And what this is it is kind of a baby's first project in neural networks. Okay. But not using the normal hello world example, because doing all right, some history here. I don't want to get anybody's hopes up, but I do want to know what you're gonna find if you do a web search for this. It's gonna be the first thing that pops up. So anyway, hello world, of course, is the joke programming like introductory thing, right? It's the example that pops up whenever you're trying to learn how to do the most simple task in a new programming language. For machine learning, the basic example that pops up, the so-called Hello World project, involves doing processing on a database of handwritten numbers. So you write the digits 0 through 9, okay, and there is a database that's named this, okay, and there's a bunch of image files of handwritten digits from different people. And the idea is that you make a computer program that goes through and learns how to identify handwritten digits so that you can create those handwritten or new handwritten digits, or give it different handwritten digits that aren't part of the ones that it tried to learn against, so that it can accurately determine which digits there are. Okay. We're not doing something that's that sophisticated, because in order to do that level of project, we would have to either write a bunch of stuff by ourselves or use a powerful thing and not really understand how it works. Okay. I don't want to do that. That's not why we're here. So instead, we're going to do another simple example, except the example that we're doing is an example so simple it tends not to be used very often, because the set of problems that it can solve is relatively limited. But it is something that we can understand all the details of. So that's why we're going to do it. Okay, but it gives us something to do. Make sense? Okay. So yeah, the question was basically doing since I was talking about handwriting recognition, doing that based on looking at digits. So just as a quick explanation, you would have, say, the number 9 written here, right? And the way that this database works is it breaks up the image into a grid. Okay, it's done in grayscale, and the idea basically is each of the pixel on or off? Okay, does it contain part of the number or not contain part of the number? Right? And then based on the patterns it detects, it would figure out whether what digit would be represented in the box. More sophisticated handwriting recognition algorithms that you would find on, say, a phone or a tablet PC or something are based on similar principles, right? It's trying to recognize activated or not activated pixels by breaking things up into a grid. And you would use a network structure like the one pictured here on the bottom of the screen to try to set things up to figure out maybe combinations of pixels being turned on represented certain kinds of features, particular loops that narrow down the category of letters that it might be, or the category of numbers. What? Yeah, the way that these programs are improved are based on this kind of process. Yeah. Okay. So the thing that we have here to be sorry, I'm starting to get frustrated with this cough of mine. I don't feel sick, and if I can not talk for 20 minutes, I'll be fine. But I have to keep talking. Anyway, the network structure here we have is based on two things. We have a list of inputs to the system, which are represented by X, and then we have a list of weights that are represented by W. And the idea, and we also have a bias, which is like one extra weight or that goes with the inputs. It's a traditional feature that I'm not going to get into the details of why it's included, but for our program and the way that things are set up, this is how things are put together. Okay. So W0 corresponds to the bias, and then W1 and X1 and W2 and X2 and so on go together. Okay, so the weights correspond to the inputs according to the index. And the basic idea here is that we take an input, we multiply it times the appropriate weight, which scales how important that particular input is to the result. Okay. If an input ends up being not important to the final answer, its weight will get smaller. If an input ends up being important to the final result, its weight grows as we refine the behavior of the neural network here. This is all fed into an activation function, which is the thing that basically measures the system or measures the inputs to generate an output. And then that output is processed in whichever way we've decided that we're going to be processing things. Okay. Typically, what happens is the activation function is some function that ranges from 0 to 1. Okay. The common types of functions that are used for this application are referred to as sigmoid functions. Odd functions that range between 0 to 1 are mostly the ideal ones. Okay, so we see that it's kind of anti-symmetric about the origin, or about x equals 0. And and after a certain point, it kind of tails off and is basically effectively 0 or effectively 1, right? And there's a middle range where it's scaled. The weights have the effect of kind of broadening or narrowing that middle range based on affecting ultimately what value x gets plugged into here, right? This x is just a scalar x. It's not the vector for the inputs. Just as a... I need you to say that louder. Yeah. For the purposes of graphing or using it, this lowercase x here is just a number. It's not a vector like it is up here. I was careful about using boldface or not boldface for vectors or scalar quantities. Okay. So the idea behind all of this is that we want to set lowercase x, the input to the sigmoid function or the activation function, as being the product of these two vectors. Okay. Now I use asterisk here because I'm talking about MATLAB matrix multiplication. Okay. So this is a row vector times a column vector. So a row vector times a column vector gives us a dot product, right? Okay, so that's why lowercase x is just a number, because it ends up being a dot product. Okay. The nice thing about the way that this is set up is that there's a lot of vocabulary and written up stuff going on here, but all we do is just do a dot product to get what number we need to pass to our activation function. And this activation function is going to tell us what the value of the output y is. Okay. Now in this, which you can think of as a single layer network, or basically a single neuron, right? All of this operation in a more complicated structure would be a simple neuron. So that whole graph on the last cell is this part here. Right? Because this thing generates an output, and that output is fed into all of the other elements here. Okay, so I realize that there's basically all of the arrows go everywhere, right? From left to right. So what we do is we have our inputs, and then those inputs feed into a layer that looks like this, right? So there are weights and an activation function as the blue part that's hidden in here. Okay. And when you're constructing a neural network, you want to have several of these neurons so that you give more flexibility to the computations being done by the network. Okay, and then these feed into yet another layer that looks like this picture again, where the inputs, instead of being yellow and green, are the outputs of this layer, right? So inputs to the system, first set of neurons processes stuff and then generates outputs. Those outputs become the inputs for hidden layer 2. They have their own biases and weights. And then a processing is done here. These activate and give outputs to, say, the two output values that we're generating for our network. Okay? Generally what happens is you have a large number of inputs. Each layer will be smaller than the previous layer, narrowing things down. And then you'll have your output layer at the end. Okay, so like for the handwriting example, you would have like a 32 by 32 image, right? And so each pixel would be an input. Okay. When you get to the output layer, the only thing you care about is what digit is it, 0 through 9. So you would have 32 squared inputs, but only 9 outputs. Or 10 outputs, excuse me. Okay. And in that particular network, all of the outputs except for one of them should be 0, right? Or numbers close to 0. You might have some numbers that look close together, like 4 and 9. So maybe it can't tell the difference between those things very well. In which case you would get two numbers that are significantly larger than 0 and the rest of them basically 0. Yeah. But that's the hardest one, okay? Some people connect the 4 at the top, some people don't connect 4. No, depends on how many children's games you played, I guess. But yeah, that's the problem. There's a couple of numbers that look close together. You can mess things up by whether or not you cross your Z. All that. Okay. Now, there is a wonderful series of videos, of which this is the first, on neural networks, if you're curious. Okay. I think there's 4 videos, and they're all in the neighborhood of 15 to 20 minutes long. Okay. It's my recommendation that you watch at least the first one, because the Grant Sanderson shows in motion what is happening here, a little bit more detail than we've talked about today. And he talks about the handwritten digit example in terms of the video, and kind of goes through the whole exercise. Does not talk about the programming details, but goes through the ideas of how one thinks about this problem and how the network is trained and all of that. But just explains it on the idea level, not the this is how you do the nuts and bolts programming stuff. Okay. Now, the version with the more connected network is what you do in general. Okay. We are going to focus on a trimmed down version of this problem. Okay. We're just going to do this. Okay. This is a single neuron. And if we think about this single neuron as a very simple neural network, it is what is referred to as a single layer perceptron. Okay. A single layer perceptron was the first neural network that was implemented by computer scientists. Okay, I think it was done by the Army or something. I think it was a military science result. Um, but it is an extremely simple neural network, okay? Its applications generally are null, okay? Um, if we want to do more complicated problems, we have to use multi-layer perceptrons. Okay, so networks that look like this, all right? But I want to keep things simple for us, so we're going to do the single layer perceptron. The idea behind a single layer perceptron is pretty simple and can be represented visually. You have a set of points. Some of those points you want to be true, and other points you want to be false. The perceptron's job is to try to distinguish between true and false. So if I set things up so that the value is a point in two-dimensional space, in addition to it having its coordinates x1 and x2, it has true or false associated with it, right? And I want to, based on x1 and x2, be able to say whether that point counts as true or counts as false. Okay. If it's true, it is going to be on one side of the line. If it's false, it's going to be on the other side of the line. Okay. Okay. So the example that's used here to start off with is the idea of an inclusive OR. Okay, so this is the mathematical OR. If I take as my four inputs false, false, true, false, false, true, and true, true, because those are my four options, right? False, false, false or false is false. True or false is true. False or true is true. And true or true is true. Okay? That's shown on the little table there. And the idea is that we represent these things as points in space, and we try to come up with a line that separates between true and false. Yeah, inclusive OR means if A or B is true, if either A or B is true. This is the exclusive OR is a different thing. We have to make sure that we are careful about that. Okay, so here is the table, or the plot, pardon me. And what we see is that the yellow points are the ones that are designated by true according to our table, and the black point is the one that is designated as false. Okay, and we can draw a line that separates between true and false based on whether we are above the line or below the line. Okay, now one of the most important things to realize about this picture is that there's not just one answer. There are many lines that I could draw that would satisfy the condition of giving me a properly trained network, right? I could change the slope of this line a little bit and still have all the yellow points above and the black point below. I can change the y-intercept some, right? There's flexibility here. Okay. I'm Sorry, what? It depends on how complicated your neural network is. So for the question was basically, is that flexibility helpful or not? Do you try to fine tune that as much as possible? The fine tuning isn't something that you have direct control over. The fine tuning is a result of how difficult your data set is. We're going to see some more difficult data sets here very shortly. Okay, so the next example here is an example of the exclusive OR. For the exclusive OR, we say that true or true is false, because we don't want them both to be true. Okay. And there is no line that I can draw that will put all of the true points on one side and the false points on the other side. It is an impossible question. Okay, there is no straight line that I can draw that gives me that separator in this case. So it doesn't make sense to try to map this as a single layer perceptron, which is part of the reason why we use multi-layer perceptrons, because we need more flexibility than that. Okay. So there's some examples here about how to use the perceptron class. We'll get into that later. And there are some methods that are written up in order to generate data. And so what we're going to do is there's going to be a few different types of just randomly generated data sets that we make. What I have done is I have written routines that make some kind of shape and then randomly plot data points inside of that shape. I do it for trapezoids, ellipses, and rings. These are just made to where we can play with this easier without having to type in a bunch of data by hand. That's the purpose of these methods. Sorry, I'm trying not to cough. If you look at these, both of these are trapezoids. Okay. Basically, what I do is you make a bounding box for the trapezoid. Like, you tell it the vertices and how many points you want to have in there. And then whether you want those to count as true or count as false. Okay. And then it makes the points. This is the number of points. These tell me where the vertices are for the trapezoid. And then this tells me if I want it to be a true value or false value. Yep. Okay. And so what you would do is the training data that you make has three components. It has x1, x2, and then true or false. Okay, so each one's a 3 vector. you make your data set, and then you pass that data set to this, which assigns it. Okay, basically says this is the train. These are all the data points that I want you to train on. And then you have a training method, and the number here is how many iterations of adjusting the weights do you do as part of the training process. So for the way that training works is you have some line that you're using. You initialize that line with random numbers, and then you run the program to see whether or not you get the right answers or not. So it checks to see are the things that are supposed to be true, and the things that are supposed to be false. Many of them are going to be wrong at the beginning, and then you make adjustments to the weights based on which ones were wrong, and then you try again. Okay, that the number in the train input is how many times do you try. You might need to do it 5 times. You might need to do it 500 times, depending on how complicated things are. All right. So here, this network is basically trained after 100 epochs. EPOCH is the way to spell the word that I just used. Epoch being a measure of time, and in a neural network and machine learning lingo, an epoch is considered to be one training cycle. So the process that I just described would be one of those cycles. Okay. The second example here is a much more difficult training set because the values overlap. So it's not possible for me to get an answer in this case that's perfect. I can do an okay job, but it's not going to be possible to get everything exact. Okay. And then this one is one that we do a better job on. Yeah. What the specific way I'm doing what? Uh-huh. Okay. Okay. All right. Let me stop you there because we're about out of time. Okay. So the question is about how am I figuring out how to place the line to try to separate these data sets? Okay. And like in this case, for this last picture here, we're a little bit mystified because the range of values that would seem to work here is relatively narrow. Okay. The answer to that question is I did jack squat to figure out where that line goes. Okay. I let the computer do it, which is the whole point. All right. Now we haven't gotten to the process of how training this works. I just want to introduce the idea of it, give you a little bit of time to digest, let you hopefully watch the video from 3 Blue 1 Brown between now and next class to wrap your head a little bit more around this neural networks idea. Okay. But we are going to get into a few of the nuts and bolts about how the training for this works. And what I'm going to, once we understand that, I'm going to ask you to do a couple of specific things to process data sets and then make up a couple of your own examples. Okay, so you're going to use these generator functions that I've made in order to produce some examples, some that train well, some that don't train well, and then how to do a more of an exotic data thing. But since we're out of time, I will save that for next class. Okay. All right. Take care, everybody. Something like that. I'm going to be, for the due dates for things, for these last couple, with Thanksgiving break, the end of the semester is just kind of wonky, so I'm not going to be too worried about that. But the quaternion and the perceptron thing are going to be our final 2 assignments, and as long as those get turned in so that I'm not worried about rushing to get grades turned in on time, I'm probably going to be okay. Yeah. No, it is my intention to be flexible here. Okay. Anyway, take care, everybody. Have a great one, and I will see you next time.